morning, dear friends. This is Namrata Atre from Computer Science and Engineering Department, IAS IPS Academy. Today we are going to discuss about error control mechanism that happens in data communication and computer networking. So, referring to OSI model, error control happens in data link layer as well as in transport layer. Data link layer is layer number 2 and transport layer is layer number 4. Both these layers are responsible to perform error control in during the communication process. But the difference between the two is that in data link layer, that is layer number 2, the error control mechanism happens from hop to hop delivery only. Hop to hop delivery means, suppose this is the sender, this is the node 1 and this is node 2, which is the receiver node. And in between there may be various intermediate nodes via which the data will be transferred from sender to destination, from source to destination. That it may not happen that data will directly get transferred from source to destination in one hop. Data will be transferred from source to destination using various hops in between, that is various intermediate nodes. This is one hop, this may be another hop, this is the traveling path of data. This is the third hop, and finally data gets transferred to the destination. So this hop to hop delivery, in hop to hop delivery, the control mechanism, error control mechanism required is provided by data link layer. That means if the source and destination in between hops wants to find out verify whether the data is erroneous or not, they will have to use the algorithms, error control mechanisms in data link layer. And on the other hand, if final source to destination data delivery, the error control mechanisms will be handled by transport layer. So there are different algorithms responsible in both the layers for the same task of error control. Now, what is error control? Error control is, what is the need of error control? Error control is when there are 5 components in a data communication system. One is the sender, other is the receiver, this is the sender, this is the receiver. Then we have channel, it is also called as medium, channel or the medium. Then we have data packets. You can refer them as packets or frames or bits or bytes of data or signals, whatever, in whatever language you can refer to the information. This is the information or the data. 1 component, 2 component, 3rd component, 4th component, and the last 5th component is protocols. Protocols are the rules which decides how this data will be transferred from source to the destination. So protocols, there are synchronous protocols which are defined at the transmitter. The same protocols will be used at the receiver as well. So these are the 5 components. Now when we see the channel or the medium, it can be wired medium or wireless medium. However is our application requirement. Whatever the channel is, either wired or wireless, the channel is bound to impair the data. When this data or this information travels from this channel or medium, it will get impaired, either in less quantity or in more quantity. Impaired means there will be some kind of distortion in the data. It can be distortion, it can be interference, it can be crosstalk, it can be attenuation. These are all impairments in the data. That means the data will get erroneous or transformed. It may be wrong data. It can become wrong data or erroneous data. So from now on, we can refer to the data which is transmitted from the transmitter is pure data, is clean data. But when it travels through the channel, it gets impaired or it gets distorted or it gets erroneous. So this erroneous data may be received at the receiver, but receiver is unaware of the fact that this data contains error or not. Receiver will think that the data is the data that it is receiving, that was only transmitted from the transmitter. But that may not be the case. That data may be pure or it may be impaired data or erroneous data. So it is very important for the receiver to be capable to identify that whatever data it is receiving is erroneous or clean, is erroneous or error free. So this capability at the receiver is provided by error control mechanisms. So this is the importance of error control in any communication network, that the receiver is unaware that whatever it is receiving is good or bad. So it has to verify whether the whatever it is receiving, the frames, data frames or the data packets that it is receiving are good to go or they should be discarded. So if they are good to go, then it will accept them, and if they are not in proper format, if they are erroneous or impaired, this receiver will discard them. Then only proper communication will happen. Because in communication, what is our requirement? The requirement is that whatever is communicated by the transmitter should be received by the receiver in exactly same manner, and it should be received by the authentic user only, not by unauthorized users. So these are the two basic requirements of successful communication. Others are all performance issues. One thing is whatever is being delivered should be correct. Secondly, to whomever the data is being delivered should be proper, authentic person. So here we are talking about the correctness of data at the receiver that is being received, the data being received. So therefore we require error control in a communication system. Now error control, that I already told, happens at two layers. This error control is provided by two layers. The function is given by two layers, data link layer and transport layer. Both has different algorithms to perform this task. Today we are going to discuss about Hamming codes. So before going to Hamming codes, let's see, there are error control. Error control consists of two terms. One is error detection and another is error correction. Until and unless we are not able to detect errors, we cannot correct them also. So it is important at the receiver that receiver should be able to detect whether the data is erroneous or not. This is the first step. Second step is to correct those errors. So there are different algorithms for both these purposes. Some algorithms can only detect errors. Some more complex algorithm can detect as well as correct those errors also. So for error detection, there are parity codes, and for error correction we have, this is one-dimensional parity, two-dimensional parity codes for error detection. This is error correction, and another is basic is Hamming code. So error detection has two things. 2D parity code is can also detect errors as well as correct them. And Hamming code can also detect errors as well as correct them. But one-dimensional parity or CRC, cyclic redundancy check, or checksum, all these codes can only detect errors, whether the data received at the receiver is erroneous or not. But 2D parity and Hamming code, these two codes can also verify as well as correct those errors. So in this lecture we'll be discussing about Hamming code. One more important terminology is there are two kind of error controls. One is forward error control and one is reverse error control. Some algorithms follows forward error control scheme and few algorithms follows reverse error control scheme. What is this? So forward error control mechanisms are those codes or those algorithms where whenever data received packet or data is found to be erroneous. So what is the responsibility of receiver? Receiver knows that whatever it is receiving is erroneous. So now receiver, when it knows that the data received is erroneous, so it will not accept that data, it will discard that data. So in forward error mechanisms, if the received data is found to be erroneous, the receiver discards that data frame. This is one way mechanism, that is forward. Forward means transmitter transmits data, receiver detects some error in that data, it discards that data, that's it. Transmitter doesn't know what happened with the data that it has transmitted. So this is forward error mechanism. But in reverse error mechanism, what happens is transmitter transmits the data frame, the receiver receives those frames. There can be two conditions. Either the data frame is correct or the data frame is wrong. If the data frame is correct, in that case, the receiver will receive the data frame. But if the error frame received is incorrect or it is erroneous, then receiver will discard the data frame and also acknowledge the transmitter back that whatever it has received was erroneous. So now it is requesting for retransmission. This is the proper way, this is the proper algorithm, because transmitter should know whatever it has transmitted has successfully received or not. This is the purpose of communication, that whatever information that we want to transmit should be successfully received by the receiver and utilized further. So this purpose can be solved using reverse error control mechanisms. So there are two types of mechanisms. Forward error control may be less complex algorithms and protocols, but reverse error control mechanisms are more complex and evolved protocols. Now, let us move towards Hamming code that we want to discuss. To learn about Hamming code, how to solve Hamming code, that means how to find out that using Hamming code method, how we will be able to find out that the received data is erroneous, first thing, and then we'll be able to, then we'll learn to find out the position of error so that we can correct that error. So let us solve an example in order to understand Hamming codes. The question is something like that: detect, generate a the question is something like generate a Hamming code word for the data 1101. So we need to solve this using Hamming code method. So now let us learn few terms regarding this error control algorithms. One thing is data word, another is code word, or we can say redundant bits, and third is code word. Data word is the data that the transmitter wants to transmit. Now, the transmitter wants to transmit some data, but it wants that the receiver should be able to find out errors, if any, after transmission. That means once this data is transmitted at the receiver should be able to find out errors in the data, if any. So this capability will be given into the data itself by the transmitter, and this process is called as coding, error control coding. So in this coding, what we have to do is, here in the term of information, we are simply talking about digital bits. We are not talking about analog signals. So the data is in the form of bits, digital bits. Now, if we have this data, suppose this is the data, original data that needs to be transmitted, and in order to use any kind of error coding mechanism in this, we have to add some extra bits, so that at the receiver, this entire ensemble that is being transmitted, the receiver should be able to find out errors in those ensemble, so that our data can be verified whether it is correct or not. For this, we need to add some extra bits in the data. This data word means the original data that needs to be transmitted, original number of bits that needs to be transmitted. So let us name it as small d. Redundant bits, redundancy means unwanted, repetitive, that we don't need. So actually transmitter don't need, neither the receiver needs these bits. There is no significance of this bit. There is no meaningful information hidden in the bit. But these bits are required in order to check, verify for the errors in the data. So we need to insert these bits into the data frame. So therefore they are called as redundant bit. So let us term them as small r. Small r is the number of redundant bits that we will be adding in the data word. The third term is code word. When these redundant bits are added into the data bits, the ensemble that is formed is called as code word. And since we are using Hamming code mechanism to perform this task, this code word formed will be called as Hamming code word. That is required in the question. If you were using CRC method to perform this error detection mechanism, then the code word that you would have generated was called as CRC code word. If you were using checksum method, then the code word that you were generating was called as checksum code word. Right? So code word is the combination, let us term it as small c. It is the combination of data bits and redundant bits. So in Hamming code method, the first step number 1 is to find out number of redundant bits that needs to be added in this data word. We are sure that small d, the value of small d is 4 because it is given in the question. The data that needs to be transmitted. So number of data bits are 4, therefore the value of small d is 4. Now we need to add redundant bit. First question is how many redundant bits you will be adding in this particular question. So that depends on the length of data bits, and that is found out using an equation. 2 to the power r should be greater than or equal to d plus r plus 1. This upon sufficing this equation only, we will be able to find out the value of r. So we will be putting value of d as 4 in this equation. Let us start by using r equal to 0, 1, 2, 3. For whichever value of r this equation satisfies, that will be the number of redundant bits that we need to add in the code word. So let us start with r equal to 0. But since r equal to 0, then 2 to the power 0 is 1. So that may not be true ever. So let us start with r equal to 1. So 2 to the power 1 is greater than the value of d is 4 plus r, value of r is 1 plus 1. So 2 is greater than equal to 4 plus 1 plus 1. This equation is not true. Since this equation is not true, therefore the value of r can never be equal to 1 for this particular question. Let us take r equal to 2. 2 to the power 2 greater than equal to 4 plus 2 plus 1. 4 greater than 7. This equation is also wrong. So the value of r can never be 2 again. Let us take the value of r as 3. 2 to the power 3 greater than equal to 4 plus 3 plus 1. Here 2 to the power 3 is 8 and the value of this is 8. So at least if this side is not greater than this RHS, but at least they are equal to each other. That means this equation satisfies. So we can say the value of r is 3. That means we need to add 3 bits in this data in order to make a code word. Because the question says you want to create a code word. So in order to create the code word, we will be adding 3 redundant bits in the 4 data bits, right? So therefore the value of c will be equal to d plus r, which is d is 4 we know in the question, plus r that we have just found out, the value of r is 3, so c becomes 7. So the code word that we will be finding will be equal to 7 bits. We will be finding a 7-bit Hamming code word for this 4-bit of data. The next step is step number 2. In first step, we have found out the number of redundant bit. Now we will be finding out the positions of these redundant bit. Where do you want to insert these bits in the data? Okay. So second step is finding the positions of redundant bit r. For this, let me create a structure. Since I know that the 7-bit Hamming code word will be created, so I am creating a frame. 1, 2, 3, 4, 5, 6, 7. You can number this question. See, there can be multiple answers for this particular question. It's the way in which you solve the question. Because this, since it is binary, so we can start from LSB to MSB, or we can number from MSB to LSB also. In both the cases, the answer will be different. The code word that you will be creating will be different. So let me take one way in which I am starting giving the numbers from LSB to MSB. So I have numbered the positions of these bits. This is my code word. This is the structure of my code word that I will be forming. Right? So here I want to place the positions of data bits and the position of redundant bit. Fine. So I don't know anything ki where I should put this data, where I should put these 3 redundant bits. I don't know that. So I need to find out. So I am finding the positions. To find the position, let me take 2 to the power n. I'll be using this function 2 to the power n, where n is equal to 0, 1, 2, 3 and so on. So when value of n is equals to 0, 2 to the power 0 is 1. So the position of first redundant, there are 3 redundant bit position that we need to find out. The position of first redundant bit is first position. Because 2 to the power 0 is 1, therefore this is the first position. And let me name the redundant bit number 1 as P of 1. In suffix we are putting 1. So first position of first redundant bit is 1 and the name of that redundant bit I am putting as P of 1. You can keep any name. But since we will be using parity check in order to find the values, therefore I am using the letter P here. Then n is equal to 1, taking n equal to 0, then n equal to 1. 2 to the power 1 is 2. That means second position, and the name of the second redundant bit will be P of 2. Similarly, n is equals to 2, 2 to the power 2 is 4. So the third redundant bit will be placed at position 4. And the name of this redundant bit will be P of 4. So we have found out the positions of redundant bit. The value of redundant bit was 3 and positions was first position, second position, fourth position. So let us place the positions. So at first position of P1 is at first position. So I am placing P of 1 here. Then second redundant bit is at P2. So I am placing P2 here. Third redundant bit is at P4. So this is the fourth position. I am placing P4 here. Right? Now in the vacant places, I will be keeping the data as it is. If you are keeping the data in the reverse order, again the code word will change. Okay, so you need to follow one process. An important thing is that you have to perform the repetitive process at the receiver also when we will be correcting the errors. Right now we are just detecting or generating the code word. When we will be finding out the errors and correcting them at the receiver, then we'll have to perform the same process, the same order at the receiver also. So this is important that you understand what steps you are performing at the transmitter so that you can repeat them at the receiver as well. So here I am putting the data bits as it is. So this is my code word. Now the third step is finding the values of redundant bits. I found the number of redundant bit, position of redundant bit and the values of redundant bit. What is P1? What is the value of P2? What is the value of P4? 0 or 1? We have to find out that. In order to find the values of redundant bit, we will be using parity code. I understand that you already know about the parity code. Parity code happens in two ways, either even parity or odd parity. In even parity, we check the number of ones in the data. The number of ones in the data should be even in number, like 2, 4, 6, 8, 10 and so on. If the number is even, that means that data has even parity. The next step is to find out the values of R. So we have to find 3 values of R. I mean, there are 3 bits, R, P1, P2, P4. We need to find out all the values of all the 3 redundant bits. So in order to find out the values, we will be using the parity code. As already discussed, that parity, there can be 2 parities, even parity or odd parity. Since nothing is given in the question, by default we have to take even parity. And if something is already specified that you have to generate a Hamming code word for the data using odd parity or even parity, then we will be using that parity only when we are finding the values of parity redundant bits. So right now nothing is given, so I'll be using even parity. Right? So even parity in order to use the parity checks, we need to find out. So let us say that the first value that we need to find out is P1. So to find the value of P1, we will be verifying even parity at specific positions only. What are those positions? So in order to find P1, we will be using positions. Since at the suffix we have 1, So we'll be starting with position number 1. So 1, taking 1 and leaving 1. Taking another, then leaving the next one. So we are taking 1, leaving 2. Taking 3, leaving 4. Taking 5, leaving 6. Taking 7. Taking alternates and in differences of 1. Right? So these are the positions at which we have to find out the value of bit, so that we can find out the parity in that. So at position number 1, what do we have? We have P1. At position number 3, we have 1. At position number 5, we have 0. At position number 7, we have 1. So this is the values at these particular positions. Now we need to find out whether the number of ones here are even or not. That means we need to find out even parity. We need to check even parity at these positions. So are the number of ones even here? Yes, there are 2 ones and 2 is an even number. So here already even parity verifies. Therefore, the value of P1 will be 0. You don't need to add extra 1 to create even parity. Even parity already exists. So the value of P1 will be 0. In the same way, let us find out P2, value of P2. In order to find out the value of P2, we need to verify parity, even parity at specific positions. Which positions? Starting with 2. So taking 2 numbers together, leaving next 2 numbers. Taking another 2 numbers and leaving further 2 numbers. So we are taking 2, 3 together, leaving 4 and 5. Taking 6 and 7, leaving further numbers, positions. So these are the positions at which we need to find out what is the value of the bit. At second position, at position number 2, we have P2, right? So we will write P2 here. At position number 3, we have value 1. So we will write 1 here. At position number 6, we have 1. At position number 7, we have again bit value 1. Now finding even parity. Is even parity verifying here? The number of ones are even? No. Number of ones are 3. 3 is an odd number. That means the value of P2 has to be 1 in order to make even parity over here. Because the question says we need to use even parity. So in order to create even parity, does not exist right now here. So in order to make even parity, we need to make the value of P2 as 1. So the value of P2 is 1. Next, we need to find the value of P4. In order to find out the value of P4, we need to check even parity at specific positions. Starting with position number 4, taking 4 in a row, leaving another 4. So when we take 4, 5, 6, 7. Further 8, 9, 10, 11 we have to leave. But the code is only 7-bit long. Therefore, we don't need to worry about further positions and the bit values, right? So we are taking 4 in a row because we have to find out the value of P4. Now, at 4th position we have P4. At 5th position we have value 0. At 6th position we have value 1. At 7th position we have value 1. Now, finding out whether the number of ones here are odd or even. So the number of ones here are already even. That is 1 and 2. 2 is an even number. So the value of P4 don't need to be 1. It will be 0 only. Therefore, the value of P4 will be 0. Why? Because already even parity suffice here. So we don't need to change the value of P4. So P4 will be 0. So now we have all the 3 values, P1, P2, P4. Now we can complete this code word. Yes, we can complete the code word. The final code word that will be generated using Hamming code method will be 1, 1, 0. The value of P4 is 0. Then 1. The value of P2 is 1. And last, the value of P1 is 0. So this is the 7-bit long Hamming code word for the data ensemble 1101. Using this ordering. If you change the order, reverse the order, this code word will change. Therefore, there can be multiple answers to this particular question. The thing that you need to keep in mind is whatever order you are following at the transmitter, the same order should be followed at the receiver also. Why do we need to work out at the receiver? When this is what we have generated at the transmitter. Now the transmitter will transmit this code word over the channel. After getting received by the receiver will check whether this data that it has received, this code word that it has received is correct or not. There can be two conditions where it will be correct either or it will be wrong. In whatever cases, the receiver will verify, and it will verify using the same process that the transmitter had performed. Therefore, whatever order you are using at the transmitter, the same order should be used at the receiver also. So let us complete this question. This is first half of the question, that is at the transmitter end. This all process is being done at the transmitter. Now we assume that the transmitter had transmitted this code word. Okay, the data is inside this code word. Receiver will receive this code word. In the case of correctness, let us assume that the receiver has received the exact same data. In that case, same process will be performed by the receiver, and receiver will find out that there are no errors. But let us assume that there is some error in this data when it is received at the receiver. So let us assume that the receiver has received, this was the correct code word which was transmitted. The receiver is receiving, this is question number A part, question number 1 A part, this is question number 1 B part. If a receiver receives a 7-bit Hamming code word 11001111. Let us assume this was the correct code word which was transmitted, and the receiver is receiving during the process of communication there was some impairment, some distortion occurring in this data, and now this data has become 11001111. There has occurred an error in the first position. Let us assume this. So the question becomes, if a receiver receives a 7-bit Hamming code word this, you need to find out, detect errors if any and correct them, right? One more thing is, Hamming code word is capable only to find out when there is single bit error in the data. If there are multiple bit error in the data, because the data cannot be small, the data is very big, it can be hundreds and thousands of bits in the data. Moreover, these bits are packetized or framed in 8-bit frame, 10-bit frame, 16-bit frames like that. But we can say that the data is very, very long. So there are two types of errors. One is single bit error, one is burst error. Single bit error means there is only one bit of error in the entire frame, whatever block of information that you are considering. 8-bit, 16-bit, 64-bit, 32-bit, whatever block of information. In that whole block of transaction, there is only one bit of error, and that is called as bit error. But when there are multiple errors, suppose this bit also get erroneous, so this becomes 0. Error means, in digital, error means 1 becomes 0, 0 becomes 1. So here let us say this position of this bit is also bit also get erroneous. Suppose this is also erroneous, so this 0 becomes 1, this was correct, 1 1, this was also. There are 3 bits in which error has occurred. So what this type of error is called as burst error. Burst error means multiple bit error, and in that case we need to find out the length of burst. Length of burst means how long is the error in your frame, in your data message. So the first occurrence of error and the last occurrence of error, that frame size is called as burst length. So here first occurrence of, if we are counting from this side, 1, 2, 3, 4, 5, 6, 7. If you are counting from this side, this is the first occurrence of error and this is the last occurrence of error. So the size of error will be 1, 2, 3, 4, 5, 6. 6 is the length of burst. Right? So, but Hamming code is capable to find out only single bit error, not multiple errors in a data. So we will be correct it. We cannot use multiple errors, right? So what we have taken, we are solving this question in the reverse order at the receiver. So this is the story about the receiver that was in the transmitter end. At the receiver, when we solve this question, we have the code, already we have the code word. We don't need to generate the code word or create the structure. We already have the values. Now, since it is already saying that 7-bit Hamming code word is received, and as I have solved the transmitter end right now, so I remember that in this particular code, how many number of data bits and how many number of redundant bit I have placed. I know this. But in general, when you don't know that, you have to start solving this question from right here, right? So you need to find out the value of D, because this what you are receiving is C, number of code bits, that is C. C is equal to 7. You know that here. And what you need to find out? You need to find out the value of D and value of R both. But in that transmitter case, the scenario was reverse. You had to find out there in the value of C. You already had D, but you don't had R. Here you need to find out both. So in order to find out both, again you have to use the equation to the power is greater than or equal to D plus R plus 1. Keeping the value of R 0, 1, 2 and so on. Whenever this equation satisfies, we will be finding the value of R. Once we find the value of R, we can easily find the value of D. How? If you have R, then the value of D will be equal to C minus R. Since C is equals to D plus R, code bits is equal to data bits plus redundant bit. So if you have redundant bit and you already have code bits in the question, you can easily find data bits, right? So, but right now I know everything, all the values. So D here I know it was 4, and by adding 3 bits, redundant bits, the transmitter might have created this code. Now I have to verify whether this received ensemble is erroneous or not. And to find out that, I will be performing the question, I will be performing same task from step number 3, verifying the values of redundant bit, right? So verifying the values, you have the structure. Please keep in mind, since I had numbered it from LSB to MSB, the same process I am using at the receiver also. If I had used here MSB to MSB numbering like 1, 2, 3, 4, 5, I need to use the same order here also, right? So I have already the code word. This is the code word. Now I need to find out verify the parity. So there are 3 redundant bits. The 3 redundant bits are P1, P2 and P4. I already know about that. If I would have not have known this, I will have to find it out using this process also again. So taking P1, the value of P1 can be verified as in the same manner. We need to take the positions, position number 1, leaving the next 2, taking 3, leaving next 4, taking 5, leaving next 6, taking 7. That's it. This is a 7-bit code only. So at these positions, I need to find out the values. At position number 1, I have 1. Then at position number 3, I have again 1. At number 5, I have 0. At number 7, I have 1. So 1, 1, 0, 1. The number of ones here are 3. 3 means odd. It is not even. That means the parity checking does not verify, and since it does not verify, so now I know, the receiver know that there is some error in the code, received code. There is some error because the parity code has violated. It has failed. यहाँ पे हमने जो parity create करके भेजा था, that parity is not being successfully received here. That means there are some changes in the bit value, and these changes are nothing but the errors. So since the parity does not verify, Therefore, the verification value of P1 will be 1. Okay, it will be not 0. Taking P2, taking the same positions, 2, 3, leaving next to, then taking 6, 7, leaving next to, and so on. Here at position number 2, I have 1. At position number 3, I have again 1. At number 6, I have 1. At number 7, again I have 1. So the number of ones are 4. 4 is even number. So even parity suffice. So therefore the verification value of P2 will be 0. Even parity fulfills. Here since even parity was not being fulfilled, therefore P1 had to be 1. Here it fulfills, therefore P2 value of P2 is 0. Taking P4 at positions 4, 5, 6, 7, leaving the next 4. We don't have any 4. So the value of P4 is 0. Position 4th value is 0. Position 5 it is 0. Position number 6 it is 1. Position number 7 again it is 1. So here number of ones are 2. 2 means even number. That means here again verification value of P4, the parity verifies and the value of P4 is 0. But since at one place the parity was not satisfying, therefore we had concluded that there are some errors. Therefore, the received code word is erroneous. This was our finding because the question says find out or detect whether the received code word is erroneous or not. So we have detected that the received code word is erroneous. And now the second step is to detect error if any and correct it. We need to correct also. We have detected the error. Now we need to correct it. And in order to correct the error, we need to find out the position of error. Okay, then only we will be able to correct it, because in the name of correction, we just have to convert the value of bit from 0 to 1 or from 1 to 0. But we need to find out which bit needs to be corrected. That means which position has error. So here we have find out the status of the received data code, that which is error or not, it is erroneous. Next step is to find out the position of error. To find the position of error, we need to read the verification value of these redundant bits from order bottom to top. That means last redundant bit was P4, then it was P2, then it was P1. So we are reading it from bottom to top and the value is 0, 0, 1. So this is in binary. We have to consider it as one ensemble. This is in binary. We need to convert it in decimal. Decimal it is 1. 0, 0, 1 is position 1. That means the error is in first position of your code ensemble. First position. So the position of error is found out by reading the verification value of redundant bit at the receiver. At the receiver, you have already verified whether P1, P2, P4, all these redundant bits are correct or not, they are satisfying even parity or not, and on the basis of that you have given them the value of 1 and 0. Now you have to read them from bottom to top. That means from last parity bit to last redundant bit to first redundant bit. So here I have written the values. This is in binary, you have to consider it as one entity. And this is in binary. Binary needs to be converted into decimal. Decimal mein this is 1. So that means the position of error is first position. That means this is the first position. And we already knew that this was the code word. This was the code word 110 0110. This was the correct code word that was transmitted. And this code word got impaired or distorted in the form of this. That means there was some change in the first bit, MSB bit. So this we have found out the position, that yes, using Hamming code word we have detected the error, and now since we have found out the position of error, therefore we will be able to correct it. So this was the wrong code word received, and the correct code word is, therefore the correct code word is 110011. There is change in the LSB bit. So LSB bit will become 0 from 1. So instead of 1, we will be writing 0. This is the correct code word that the transmitter had transmitted. So this is the correct code word. And this is how, using Hamming code method, we can detect errors and correct them. But it is important, both these tasks are performed at the receiver only, detection as well as correcting that. But this is possible only when you are creating a code at the transmitter end. If you were transmitting this data simply, then the receiver was not in a position to find out errors in this data and correct them. It did not know what the data was transmitted. But in order to make the receiver capable of detecting and correcting errors, it is important that we code the data at the transmitter. And this is called as error control mechanism. And the method that we are using here is Hamming code. Thank you.